Hi everyone, welcome to the lecture for week 6. This week we'll be looking at what I think is some of the most fascinating material in decision theory, some of the most fascinating material we'll cover in this unit. We'll be looking at some puzzles that arise for expected value theory and also for the other theories we've considered. Puzzles involving very large values, some even involving infinite values. And some philosophers have thought that these are genuine paradoxes, that they're irresolvable, while many other philosophers have considered these particularly strong arguments against one theory or against another. And those puzzles, or paradoxes if you like, those include, first, Pascal's wager, which came up in the workshop exercises in week 1. Second, the St. Petersburg game, which we haven't seen yet. The Pasadena game, which you almost certainly haven't heard of before. So first, we're going to look at what sort of problems these three cases pose for decision theory. Then we're going to look at how we might avoid those problems. And then we're going to look at a closely related problem called fanaticism. And at least one argument why it's not really a problem, it's just a true implication of decision theory. But you'll see what I mean by that when we get to it. Okay. First, remember expected value theory. So here's the official definition that we had, which hopefully looks pretty familiar. And crucially, remember that this theory and the verdicts it gives us rely on a notion of value. So not just any old utility function, but rather a specific value function that we have to use. What's value? Well, remember that it's a measure of how good each outcome is. Specifically, how good it is according to whatever account of goodness we're using to evaluate outcomes. So perhaps given by our normative theory, whatever normative theory is true. And that might be a moral theory, it might be a theory of what we prudentially ought to do, it might be an aesthetic theory, whatever. So for example, on the moral theory of utilitarianism, how good an outcome is, how much value it has, is just how much pleasure is experienced in the world in that outcome, minus how much pain is experienced. And of course, this is weighted by the number of people experiencing pleasure and how long they experience pleasure or pain. So value is then the sum total of how many seconds of pleasure are being experienced overall, minus the sum total of how many seconds of pain are experienced. Or for another example, if we're considering what we prudentially ought to do, what's good for you yourself, for prudential decisions, on a view called hedonism, value is how much pleasure you feel minus how much pain. And there are other theories of how you ought to make decisions for the sake of yourself, but this is just one that's quite similar to utilitarianism. Okay, but for now, keep in mind theories of goodness like these two, where goodness or value is simply how much of some quantity there is in the world, such as pleasure minus pain, or something like that. Okay. Well, what does it look like on theories like this when there's an infinite amount of that quantity? So on utilitarianism, what if there are infinitely many people experiencing pleasure? Or on prudential hedonism, what if you experience pleasure for an infinite duration, perhaps going to heaven and living an eternal afterlife of bliss? Well, if that's possible, then theories like these have to say that those outcomes, where you've got infinitely many people experiencing pleasure, we've got an infinite duration of pleasure, that those outcomes have a value higher than any finite number, any finite value. That is, such theories must say that those outcomes have infinite value. And mathematically speaking, there are different ways that you could represent infinite value, different sorts of numbers that you could place on different infinite quantities. But here's one simple way to represent infinite value that we'll focus on for the most part. So a simple way this might work is that the different values an outcome can take come from what are called the extended real numbers. And that just is the real numbers. So every number, minus 1, 0, 1, a half, all the numbers that you can have along the number line, plus two more numbers. Something called infinity and something called negative infinity. And this big blocky R is the symbol for the real numbers, all of what we usually consider to be numbers. And an important thing about using the extended real numbers, where we just have one positive infinite number and one negative infinite number, is that since multiplying an infinite number by a half, or by 1 in 100, or multiplying it by 2, multiplying it by any positive number is still going to be an infinite number, given that there's only one positive infinite number, infinity times a half has to still be infinity, or infinity times 10 still has to be infinity. So infinity multiplied by any positive number is still infinity. And you don't really need to worry about why this is true or to prove it or anything, but it will be an important fact in the case we're about to consider. Okay, so now we can move on to those three problem cases, those three puzzles for expected value theory. The first one is known as Pascal's wager, and it has already come up once, although so far it's come up only in a kind of simple form where statewise dominance applied. We're going to be looking at a slightly more general version of the argument. So this is Pascal's wager as Pascal presented it in 1670. In perhaps the first instance of someone explicitly trying to use decision theory. And note that, as you'll see in your reading, Pascal actually presented several different versions of a wager argument, or several different arguments for wagering for God. And in the reading, this one is labeled the argument from generalized expectations, which is the one that is most interesting for our purposes. Okay, so how does it go? Pascal tells us that the Christian God is, or he is not. So we have two states. But to which side shall we incline? As in, which of these should we believe? We seem to face a decision. If God exists and you believe, then there is an eternity of life and happiness. And this being so, if there were an infinity of chances of which one only would be for you, and don't worry about that bit where he talks about an infinity of chances, he's just using confusing terminology and we can ignore it. He goes on to say, you would still be right in wagering 1 to win 2, and you would act stupidly being obliged to play by refusing to stake 1 life against 3. So what he's pointing at just there is endorsing expected value reasoning. In fact, he's saying that you would act stupidly if you didn't act in accordance with expected value theory. And he goes on to extend this to cases where you can win infinite value. So in a game of which out of an infinity of chances there is one for you, don't worry what that means, if there are an infinity of an infinitely happy life to gain. So he's saying that given this sort of expected value reasoning, you should be willing to wager 1 to win an infinite value. And in the decision of whether or not to believe in the Christian God, he says, there is here an infinity of an infinitely happy life to gain, a chance of gain against a finite number of chances of loss, and what you stake is finite. And again, the terminology is quite confusing here, but the basic point is that if God exists and you believe in him, you're going to get an infinite payoff, you're going to have an infinitely happy, infinitely long afterlife, and you only have to pay a finite price to play. This finite cost of making yourself believe, perhaps going to church every Sunday, or doing the things that go along with being a good Christian, I guess. He then says, it is all divided. And wherever the infinite is, and there is not an infinity of chances of loss against that of gain, there is no time to hesitate, you must give all. The basic claim being that taking an act that has any probability of value infinity, of infinite value, that act is better than any probability of finite value. It's instrumentally better, as expected value theory says. Okay. Now, it may be helpful to put this case into a decision matrix. So we've got two possible acts here. One is believe in God, the other is don't believe in God. Or if you think that we don't really have a choice about what we believe, you can think of this as worship God or don't worship God. And there are two possible states of the world that are relevant here. Either God exists or God doesn't exist. And again, this is specifically the Christian God. And then here are the payoffs if you believe in and or worship God versus not believing in or worshiping God. Which we might color in like this. So the very best outcome we could get is if God exists and we believe in him, well then we get to go to heaven. We get to have this eternal afterlife of bliss, we're told by the Christian Bible. And if we believe in or worship God and God happens not to exist, then that's kind of inconvenient. You're waking up early every Sunday to get to church. I gather that's involved in being a good Christian. So that's somewhat costly. But it's only moderately costly for the duration of your earthly life. It would be nowhere near as great a cost as, say, missing out on an infinitely happy, infinitely long afterlife. Meanwhile, for the second option of just not believing in or worshipping God, either way, you gain or lose nothing. And I've left a little asterisk there because you might think that, actually, no, this outcome here would be something different, but we'll get to that in a sec. But just considering the decision construed this way, for now, what does expected value theory say? Well, take the expected value of believing in God. If this outcome has infinite value, then the expected value will be probability p times infinity plus probability 1 minus p, the remaining probability, times minus some finite number. And of course, that's going to be infinity. Now, what's the expected value of not believing in God? Well, that's just 0, if gaining and losing nothing has value 0. So, in this case, with a value function that says this is infinitely valuable and this is only finitely negatively valuable, and this has value 0, expected value theory will say that you are required to believe in God, or to worship God, if that's what we're considering. And in fact, you're required to believe in God no matter how unlikely it is that God exists. As long as p is greater than 0, it could be 1 in a trillion, it could be 1 in a trillion, still you would be required to believe in God because the potential payoff is just so high. It's an infinitely long afterlife of pure bliss, apparently. So basically, Pascal recommends this. Turn away from having a maximally happy earthly life and just pursue tiny probabilities of infinite value as we have here, if God happens to exist. Okay. Now you could spell out the case slightly differently if you wanted, but you don't necessarily have to make the argument work. So you could spell it out this way. So I'm told that the Christian Bible says that if God exists and you're not a good Christian, then you're going to go to hell for eternity, and it's going to be quite unpleasant. And then the value of this outcome might be minus infinity. And then believing in God has expected value infinity, and not believing in God has expected value negative infinity. So again, for similar reasons, believing in God has greater expected value. But for the argument, it doesn't really matter which of these ways we model the decision problem. Okay. But does this argument work as an argument for wagering for God, an argument for believing in God? Well, there are a whole bunch of possible objections, many of which you'll see in the reading this week by Hayek. So here are some of those possible objections. The first is that, well, this is a decision for believing or not believing in something. And you might think, going back to week 1, that, well, that's a question of theoretical rationality, not a question of practical rationality. In fact, you might think that our beliefs aren't kind of chosen. We just happen to believe things. We don't get to choose to believe things. And so this just shouldn't be treated as a decision problem. It just is the case that we believe in God or we don't believe in God. Well, if so, there is still another decision you might face here, even if you agree with that, and that is whether to worship God, this God that you may or may not believe in, or to not worship God, who you may or may not believe in. And as long as the Bible says that worshipping God is enough to get you into heaven, as long as you do the right things, regardless of what you believe, then you'll get into heaven, then great. We still face the same sort of decision here. And even if the Bible doesn't say exactly that, there's always some probability that the Bible is wrong. And so, in fact, there is some non-zero probability that God exists, and it's enough to worship him in order to get into heaven. So you could still run a similar argument in favor of worshipping God. Okay, second objection. You might think this decision matrix, this way of spelling out the case, is wrong because actually there's no probability p that God exists. Perhaps p equals 0. And then this first act no longer has infinite expected value. It just has negative finite expected value. And actually this objection is pretty compelling if the probabilities we care about are propensities or frequencies or perhaps credences, because any of these could assign probability 0 to God existing. At least if it's physically impossible for God to exist, or no God has ever existed, or you're just absolutely certain that God doesn't exist. So if we're talking about those sorts of probabilities, perhaps the argument doesn't work. Another possible objection is that, no, the correct value function would actually only give finite value to this outcome here, where you gain an eternal afterlife of bliss. And yeah, that would block the argument. That would mean that believing in God only has finite expected value. And if the cost is high enough, then you shouldn't believe in God. But that objection, that response, won't work on all normative theories. So as we saw before, this prudential theory of hedonism that says you should just maximize the amount of pleasure you experience minus the amount of pain, well, that theory is going to have to say that, yes, this outcome has infinite value. Okay. Another quite neat objection is called the many gods objection. So Sure, this argument sounds compelling, but wouldn't believing in some other god, like the god of Islam or various gods of Hinduism or of other religions, wouldn't that also have infinite expected value, since they may also reward you with an infinite afterlife of bliss? Well, yeah. And perhaps even going beyond that, we can imagine a hypothetical god that rewards you for not believing in any gods or not worshipping any gods. If there's some probability of that hypothetical god existing, then in fact, not believing in any god would also have infinite expected value. So in practice, you may well think that this way of spelling out the decision problem is not realistic. It's not the right one. In fact, we have many more options of believing in other gods. We have many more states of different gods existing, and all the acts there have infinite expected value. So believing in or worshipping the Christian god is not strictly preferred to all of the others. Maybe, maybe not. And there's a further really interesting objection, which we could call the eat a burger instead objection. And it goes roughly like this. Well, first, consider another act, flipping a coin, and committing to, if the coin lands heads, then believing in God and worshipping like a good Christian. Now, what's the expected value of this act? Well, it too has infinite expected value. It's basically like this first one, believe in God, but with an even lower probability p divided by 2. But since that still has some non-zero probability of resulting in this outcome here that has infinite value, that act is also going to have infinite expected value. So it seems like Pascal's argument doesn't actually justify exclusively just believing in God, but rather it would justify taking any act that has any probability of leading you to believe in God. For instance, going and eating a burger. After all, there's some probability, you might think, that if you go and eat a burger, you'll then be struck by inspiration and then believe in God. So likewise, going and eating a burger, you might think, has infinite expected value, just like directly believing in or worshipping God. So yeah, this objection too seems to undermine Pascal's argument for, in practice, believing in God. But neither this objection nor any of the other 4 objections undermine this kind of general implication of expected value theory, that if we face a decision situation like this, where these are our only 2 acts, and one of the acts has some non-zero probability of infinite value, we're required to take that act over the other one. In fact, we're required to take it no matter how low this probability is, and no matter how great the finite cost we would have to pay. And why is that a problem? Well, first, you might think that that verdict is counterintuitive. So we're required to wager for God no matter how tiny p is, or required to gamble for infinite value, no matter how tiny the probability. That may seem counterintuitive. Also counterintuitive that we would be required to, no matter how high the costs. In fact, that may seem kind of fanatical, and that's a semi-technical term that philosophers often use nowadays to describe what's wrong with Pascal's verdict here. And we'll see some more about that later on. So that's one problem raised by Pascal's wager and decisions of this form. There's also another one. So consider again that coin flip option where you flip a coin, and if it's heads, you then believe in God and so on. But we'll modify it slightly such that if the coin lands tails, then you do something else. So if it's tails, you just worship a tree stump. You worship something that is definitely not going to give you any, infinitely great afterlife in heaven. So we've still got our first act of just believing in God, and our second act now is flip a coin. If heads, believe in God. If tails, worship a tree stump. So if God exists and the coin lands heads, again, you get eternal afterlife. If God exists and the coin lands tails, then you're worshipping the tree stump, and let's suppose that is also quite costly, so you're incurring moderate costs during your earthly life, but then you're getting no afterlife. If God doesn't exist and the coin lands heads, you incur moderate costs, and likewise over here, you incur moderate costs. Because either way here, you're worshipping some deity that doesn't exist, and you're going to a fair bit of effort to do so. Okay, now expected value theory would say that both of these acts have infinite expected value. So they have equal expected value. So they're equally preferred. But there's a problem with that. So yes, this act here still has infinite expected value. And the problem is that in saying that these 2 acts are equally preferable, expected value theory is then violating dominance, either statewise dominance or stochastic dominance. Because notice, the outcomes here, for the first act are the same as the outcomes here for the second act, except in this state, this act has a strictly preferred outcome. So statewise dominance would say, believe in God. Don't flip a coin and possibly believe in a tree stump. And likewise, stochastic dominance would say the same thing, because it's a strengthening of statewise dominance. And yet, expected value theory says something different. So in this setting, once we've got infinite values at play, if that's a possibility, then expected value is no longer a strengthening of these other principles, rather it contradicts these principles. Yeah, at least if we can have infinite value, and also at least if we only represent infinite value with a single number that we call infinity. And actually, there are proposed ways around this objection, and those solutions are basically of the form, well, represent infinities with more complicated mathematics. You can have multiple infinite numbers, etc., and you end up saying that acts like this have a higher infinite value than acts like this. But we're not going to delve into those solutions here. Basically, with this somewhat simplistic picture of what an infinite value is, we have this problem here that expected value theory contradicts statewise and stochastic dominance. So yes, Pascal's wager gives us these two objections to expected value theory. And perhaps worth knowing, just as a bit of context, within philosophy, Pascal's wager is no longer taken too seriously by many philosophers of religion as an argument for believing in God or for worshipping God, largely due to the various objections that we saw just before, but it is still taken seriously within decision theory as a general puzzle for expected value theory and other decision theories. And later on in this lecture, we'll see a more modern version of the Pascal's wager case that has animated a lot of discussion in modern decision theory. Okay, so that was Pascal's wager, our first problem case for expected value theory. Here's the second case, the St. Petersburg game. So with Pascal's wager, you may have thought that the problems came from allowing infinite value. If outcomes just couldn't have infinite value, then we wouldn't have any problem. Or perhaps, if you like, the problem was with representing infinite values with just a single number infinity. And various philosophers have proposed represent infinite values in a slightly more complicated way, and we can avoid most of what's problematic about Pascal's wager. But we're still going to have another closely related problem, as demonstrated by the St. Petersburg game, originally thought up by Daniel Bernoulli many centuries ago. So here's a little story. While strolling the streets of St. Petersburg one night, you're approached by a mustachioed gentleman in a top hat, and he offers you a bet. He's going to toss a fair coin until it first lands heads. If it lands heads on the first toss, you get an outcome valued at value 2. If it first lands heads on the second toss, then you get an outcome with value 4, and so on. For any number of tosses n, if the coin first lands heads on the nth toss, then you win an outcome with value 2 to the power n. And we can put that bet, the St. Petersburg game, in a decision matrix like this. So if you accept the bet, if you play the St. Petersburg game, and he starts flipping the coin, and it lands heads immediately, which has probability half, then you gain value 2. If it lands tails on the first toss, and then heads on the second toss, you get value 4, probability a quarter, and so on. So for any number n, if you get n minus 1 tails, and then on the nth flip, you get heads, then you get value 2 to the power n, or 2 times 2 times 2 times 2, n times over. Okay, that may sound like a perfectly fine bet. The only kind of strange thing about it so far is that it has an awful lot of states. In fact, it has infinitely many states, since it could take any number of flips to first get heads. It becomes less and less likely that it will take that long to get heads, but nonetheless, it could take 1,000,000 flips to first get a heads. It could take 1 trillion, and so on for any natural number. So here's the case again, and let's see what expected value theory says about a bet like this. Calculate the expected value for the bet, so it's a half times value 2, plus a quarter times value 4, plus an eighth times value 8, and so on. And the reason the game is designed with value 2 to the power n for getting the first heads on the nth toss, that's because 2 to the power n divided by 2 to the n is going to be 1, no matter how big n gets. So the expected value becomes 1 plus 1 plus 1 plus 1, and so on. You have infinitely many ones being added up. So what's the expected value? Well, adding up these ones is going to approach infinity. And if you were going to assign any number to what all these ones add up to, it would be infinity. But for technical reasons, that's maybe just slightly controversial, so it's fine to just say that whatever this adds up to, it's going to be larger than any finite number. Because for any finite number, we can just pick the first, gazillion ones, or however many ones it takes to be bigger than that finite number, and this expected value then has to be bigger. Okay, so this game has expected value greater than any finite value. So what does expected value theory say about this game? If you had to pay $1 million to play this game, or you had to forego saving 1 million lives to play this game, expected value theory would say you should. Should you be willing to pay value 1,000? By expected value theory, yes. Should you be willing to pay value 1 million? Yes. Likewise, you should be willing to pay any amount of value to play this game. And you might think, well, that's pretty counterintuitive, especially since you're almost certainly going to win a fairly small amount. Probability of half, you're only going to get value 2. Probability 3/4, you'll get at most value 4. Probability 7/8, you'll get at most value 8, and so on. Once we're kind of down here a fair way, what's the probability that you win more than value 100? Well, it's minuscule. It's a tiny, tiny probability that you win very much at all. So saying that it has expected value infinity, that you should be willing to pay any finite amount of value to play it, well, that seems like too much. Okay, so exactly what's the problem with what expected value theory says about the St. Petersburg game? Well, first problem is the verdict just seems counterintuitive, you may think. We're required to pay any finite amount to play when we'll almost certainly win less than value, say, 8 or so? Seems counterintuitive. And it's even more counterintuitive that we would get the same verdict if we weren't choosing to play the St. Petersburg game, but instead choosing to have a tiny probability of playing the St. Petersburg game. So the same verdict would hold for just having a tiny probability of playing this game. For instance, like this. So an act, tiny chance of St. Petersburg game, probability 999 out of 1,000, that then you don't play the game, you get 0 value. And then the remaining probability, 1 in 1,000, is then the St. Petersburg game. And then you get such and such values. So this too has that same expected value that is larger than any finite number. And it seems even more counterintuitive that you would be rationally required to pay any finite amount to play this game when you almost certainly won't gain much value at all. So yes, even having a tiny probability of playing the game has infinite expected value. So that was one problem. Here's a second problem. The St. Petersburg game again reveals that expected value theory violates statewise dominance. At least it violates it when we're talking about acts with infinitely many outcomes, like this one here, St. Petersburg. And to see it violate statewise dominance, consider this second act, which we can call the Petrograd game. What's the Petrograd game? Well, it's just the St. Petersburg game, but we've added value 1 to every single outcome. So as the colors suggest, in every state, the Petrograd game is strictly preferred. So statewise dominance would say, yes, the Petrograd game overall has to be strictly preferred. But does expected value theory say that? No. Both games have the same expected value. Effectively, their expected values are the sum of 1 plus 1 plus 1 infinitely many times, and the Petrograd game is that same sum plus an extra 1. It's still infinitely many ones added up. So same expected value, you would sensibly assign both of them expected value infinity. Yet statewise dominance says that Petrograd is strictly better, as would stochastic dominance. And this might be a little bit of a surprise, especially since I think I said a few weeks ago that expected value theory is a strengthening of statewise or stochastic dominance. Well, it is if we're just talking about acts with finitely many states and finitely many outcomes. So expected value theory is a strengthening of statewise dominance in the context of acts with finitely many outcomes, or otherwise with outcomes whose values don't get arbitrarily large. But in full generality, when we're also talking about games like St. Petersburg, well, no, expected value theory is not a strengthening of these principles. In fact, it conflicts with them. Okay. Here's another problem revealed by the St. Petersburg game. It also shows that expected value theory violates what's known as the sure thing principle, which has been mentioned in a previous week in the Broom reading as another name for independence. Here we mean something slightly different by it, but you can see the problem even without knowing exactly what the principle is. So first we'll just see what the problem is. So consider two St. Petersburg games played with different coins. Call them St. Petersburg Game A and St. Petersburg Game B. And suppose you choose to play St. Petersburg Game A. Well, then let's consider each outcome you might get. For example, gaining value 2, the very first outcome over here. Now, conditional on the game you chose, St. Petersburg Game A, giving you value 2, would you then wish that you had chosen Game B instead? Well, yeah, because conditional on St. Petersburg Game A giving you that outcome of value 2, St. Petersburg Game B still looks like a full St. Petersburg game. Because they're run independently, the conditional probability that St. Petersburg Game B gives you such and such outcomes, it's the same as the unconditional probability that it gets you such and such outcomes. Because its probability of getting you, say, value 8, it doesn't depend on what St. Petersburg Game A gave you. And we can kind of illustrate this in a way that disclaimer is not going to be a proper decision matrix, but still gives the basic idea. So St. Petersburg Game A, and here are the states for St. Petersburg Game A, you get such and such values. Now in that state where you get heads in St. Petersburg Game A, what does St. Petersburg Game B look like? Well, it's just the full St. Petersburg game. Meanwhile, in the second state, if you get heads on the second toss in St. Petersburg Game A, because St. Petersburg Game B is independent, you've still got the full St. Petersburg game. Okay, and again, remember, these are not outcomes. These are entire gambles, so this is not a decision matrix. But we can kind of color in what happens in each of these states for St. Petersburg Game A. So in each of those states, you gain some amount of finite value, and that's well and good. But conditional on getting that state, St. Petersburg Game B still has infinite expected value. So suppose you took St. Petersburg Game A, you flipped a coin a few times, and you ended up getting value 4. Would you then prefer to switch to St. Petersburg Game B when you don't yet know how many coin flips it took to come up heads in that game? Well, yes, because it still has infinite expected value. And in fact, that holds for every single way that St. Petersburg Game A could turn out. So conditional on gaining such and such value in A, you would prefer St. Petersburg Game B since it has infinite expected value. Basically, no matter how St. Petersburg Game A turns out, you would then prefer to swap it for St. Petersburg Game B. And in fact, you would prefer to swap even if it costs a huge amount to do so, because this is infinite expected value. So paying any finite amount of value would still be worth it to get that infinite expected value. Okay. And this, you might think, seems irrational. If you choose that act and then you find out the outcome, you would then prefer to switch to the other act and pay any finite amount, perhaps pay $1 million, sacrifice or forego saving 1 million lives in order to play the second game. Likewise, if you'd chosen St. Petersburg Game B, because they're just the same game using different coins, no matter how St. Petersburg Game B turned out, you would then prefer to swap for St. Petersburg Game A, unless you already knew how the coin turned out. So that seems kind of odd. So I now have an excuse to use this meme again. You may have chosen one St. Petersburg game, but you will always be the distracted boyfriend looking over at an identical St. Petersburg game. And likewise, if you'd chosen this one, you'd be looking back at the first one, again being the distracted boyfriend. Okay, so in more formal terms, what's going on here, this kind of seeming irrationality, is that expected value theory is violating what's known as the sure thing principle, which in this setting means if there's some list of events that carves up all the possibilities, and this list of events, it might not be the same as the states, but here those events are the states determining the outcome of St. Petersburg Game A. So that carves up all the possible ways the world might turn out. And if one Act A is strictly preferred to another Act B, conditional on each one of those events, not states, but events, as it is here, where St. Petersburg Game B is preferred to St. Petersburg Game A in the event that St. Petersburg Game A gives you value 2, if we have that, and one act is preferred to the other conditional on each such event, then that act is strictly preferred. So St. Petersburg Game B is strictly preferred to the first one. And that's often called the sure thing principle. And in the simpler context that we've been focusing on, where you don't have infinitely many states like this, the sure thing principle is equivalent to independence if you've also got transitivity and completeness. But anyway, it's closely related to independence. So yeah, here the events in question are the states of St. Petersburg game A, and the shortening principle implies the St. Petersburg game A is strictly referred to St. Petersburg game B, or the way we've drawn it here, it looks like St. Petersburg game B is preferred to St. Petersburg game A, but the shortening principle implies both, and so it implies a contradiction. So expected value theory combined with the sure thing principle is giving us a contradiction. So expected value theory is incompatible with the sure thing principle once we're dealing with acts like the St. Petersburg game. Okay, so here were the three problems that were brought out by the St. Petersburg game. The first, we get some counterintuitive verdicts when we're comparing the St. Petersburg game to finite values. Second, we're getting violations of statewise dominance. And third, we're getting violations of the sure thing principle. And you might think that any one of these three is pretty problematic for a decision theory. So each of these is a possible objection to expected value theory. Okay, that was the St. Petersburg game. Now for the third problem case. So consider now the Pasadena game. And this comes originally from a paper by my former PhD supervisor, Al Hayek, and a student of his called Harris Nova. So imagine you're now in sunny Pasadena, a suburb of Los Angeles. And while strolling the streets of Pasadena one day, you're offered a bet by a man in a very loud Hawaiian shirt. We can call him Crazy Al. He's going to toss a fair coin until it lands heads. If it lands heads on the first toss, then you get an outcome valued at value 2, according to this bet. And if it first lands heads on the second toss, you get an outcome with value -2. And you may not immediately be able to see the pattern because the pattern is quite complicated, but basically for any number of tosses n, if the coin first lands heads on the nth toss, you win an outcome with value -1 to the power n-1 divided by n. And don't worry too much about the details of this equation. They don't really matter as long as they get us the numbers in this table, which happen to be gaining value 2, losing value 2, gaining value 8/3, losing value 4, and so on according to that equation. And these values are going to cause problems similar to the problems we saw with the St. Petersburg game, but slightly different problems. So here's the game again, the Pasadena game. And let's try to take the expected value of it. Well, probability of half times value 2 plus probability of quarter times value -2 plus probability 1/8 times 8/3, and so on. We get this long equation. And if we were to simplify each of these probability times value pairs, it becomes 1 minus a half plus a third minus a quarter plus a fifth. And any maths aficionados may recognize this as the alternating harmonic series. But all you really need to know about this series is that if we add it up in this order, it ends up being approximately 0.69. As we add up more and more terms, it gets closer and closer to 0.69. But we could add it up in a different order, and then we would get a different number that it approaches. In fact, add it up in an order of your choice, and you can make it approach any number you want. So this sum here, or the expected value of this game, it doesn't have any fixed number. You can't say that it has expected value 0.69, but not expected value 0 or expected value 100. Either it has all these expected values at once, or it has none of them. Its expected value really is just undefined. It doesn't have one. So, how do we evaluate this game? Is playing the game better than having value 1 for sure, or having value 1 million for sure? Well, expected value theory can't say. Expected value theory doesn't give you a preference ranking for this game, this act, versus any other act or any other outcome. And in fact, it's not just this act, the Pasadena game, that has no expected value. Having any probability of playing the Pasadena game also has no expected value. So expected value theory also can't say how to compare an act that has the slightest chance of giving rise to the Pasadena game. It can't compare that to any other act. So what's the problem here? Well, the main problem that we've just seen is that the Pasadena game reveals that expected value theory violates completeness. It doesn't always give an answer, at least once we're dealing with games like this that have infinitely many possible outcomes. It also, again, reveals a second problem. It demonstrates, again, that expected value theory violates statewise dominance. How does it demonstrate that? Well, to see this, just compare the Pasadena game to the Altadena game, which is the Pasadena game where we've added value 1 to every outcome. And this too has undefined expected value. So we most certainly cannot say that the Altadena game is strictly preferred to the Pasadena game, even though it state-wise dominates the Pasadena game. In every state, it's strictly preferred, but nonetheless, expected value theory can't say that overall it's strictly preferred. So we're violating state-wise dominance again. Okay, so we saw these three problem cases, and we saw that each of them pose problems for expected value theory. Now, how should we respond to that? How should we resolve those problems? Is the right response to just reject the theory in favor of perhaps one of the other theories we've learned about over the last 5 weeks? Perhaps, but that depends on whether those theories face the same problems. If those other theories face the same problems, then this isn't an argument against merely expected value theory, it's an argument against every theory that we've looked at. So do those theories face the same problems once we apply them to these three tricky cases? Well, first, take expected utility theory. Here's the definition that will be familiar from past weeks, and let's see what it says in Pascal's wager. Let's suppose we have a utility function that assigns utility 100 to this outcome here, where you get an eternal afterlife of bliss, and assign whatever finite utilities you want to these other outcomes. Well then, this first act, believe in God, has only finite expected utility, and that's going to solve a whole lot of problems. Because then if P, the probability P, is small enough, this act down here, not believing in God, will be strictly preferred. So we can avoid the verdict that believing in God, worshipping God, is always strictly preferred no matter how small P is. And this actually also allows us to avoid the second problem we saw before raised by Pascal's wager. So the first problem was we get some counterintuitive verdicts. The second problem was that in versions of Pascal's wager, expected value theory violates state-wise dominance. By using expected utility theory and having a utility function where this infinitely good outcome gets finite utility, we also end up not violating state-wise dominance in the sort of case we looked at before. And I won't go through and kind of demonstrate that here. If you're curious, go back to the case from earlier and try applying this utility function, and you'll see that actually we avoid that problem. But just to say, yes, expected utility theory with such a utility function can avoid both of the problems we saw earlier with Pascal's wager. Now, what about the St. Petersburg game? Well, here's the St. Petersburg game from earlier. And let's suppose we have a utility function like the utility of having a certain value is the square root of the amount of value. Well, then, if we calculate the expected utility for the St. Petersburg game, it becomes a half times the square root of 2 plus a quarter times the square root of 4, and so on. And if we put all that into a calculator, we end up with this sum converging to or approaching about 2.4. So the expected utility of taking the St. Petersburg game with that utility function is about 2.4. And you might notice that's not very big. So on expected utility theory with this utility function, should you be willing to give up value 1,000 in order to play the St. Petersburg game? Well, no, because the utility of value 1,000 is something between 10 and 100, and the expected utility of playing the game is only 2.4, so it's not worth it. But even with that utility function that allows us to avoid saying this game, the St. Petersburg game, has infinite expected utility, we can generalize the kind of problem of the St. Petersburg game. We can replace the St. Petersburg game with a version that causes problems even with this utility function. And we do that by just changing these values. So I've made the value in this first state twice as big. I've made the value in this second state 4 times as big, and so on. So we've actually now got this formula here for what value we get in each state. And if we try and take the expected utility of this new generalized St. Petersburg game using the utility function from earlier, u of v equals the square root of v, then with this generalized version of the St. Petersburg game, we get the same sorts of problems. So the expected utility is now a half times the square root of 4 plus a quarter times the square root of 16, and so on. And you might notice that this is just 1 plus 1 plus 1 plus 1, which is going to be larger than any finite number. So just like with expected value theory earlier and the original St. Petersburg game, expected utility theory with a utility function like this in the generalized St. Petersburg game is still going to have all of those problems we saw before. So at least with that utility function, we haven't solved the problem. Now that's not to say that expected utility theory can't solve the problem. Just it can't with that utility function we just saw. We need a different utility function. So in fact, to avoid the problems, to give unproblematic answers when dealing with these three types of cases, expected utility theory is going to need to give us finite expected utilities for all acts, including the St. Petersburg game, including Pasadena, including Pascal's wager. And we can only ensure this on expected utility theory if the utility function that we use is one that is what we call bounded. Now what does that mean? Well, it means that there is some maximum utility such that no outcome ever can have higher utility than that. And likewise, there is some minimum utility for which no outcome can have lower utility than that. So the utility function has to kind of cap out at a certain point. It can't just keep on going up and up, or at least it can't go up with no bound. And likewise, it can't go down and down with no bound. So any utility function that we're going to use that's not going to suffer from the problems of the St. Petersburg game and Pascal's wager and so on, it's going to need to look like this, where we can draw some horizontal line, some kind of maximum utility, and the function is always going to stay below it. It might keep on going up. In fact, it's going to have to keep going up if it's going to represent our preferences, and if we care about value, at least. But it's going to have to go up slower and slower and never actually reach this line, this upper bound, we could call it. And also, on the negative side, the utility function is going to have to look like the reverse of this. So there's also going to be a lower bound, but I just haven't included it in the diagram for simplicity. Okay, so one thing that having a utility function like this will mean, if you think back to week 4, is that we're often going to be risk averse. So because it's the utility function, to avoid going above that line, it's going to have to be concave for quite a lot of the possible values. We're going to be risk averse once we're kind of in that realm of different values. And in general, for expected utility theory, to avoid all of the problems we've been looking at, we're going to have a utility function like this. We're going to have to be risk averse some of the time. We're also actually going to have to sometimes be risk seeking when we're dealing with negative utilities, if we can have negative utilities. But the basic point is we're going to have to sometimes have certain risk attitudes. So just as an example of the sort of utility function that we could use that would give us this and would therefore give us finite expected utilities and would therefore give us unproblematic answers in each of these three cases and would avoid the generalized St. Petersburg game that we just saw before. An example of a utility function that would do this is this slightly complicated one, which is going to look roughly like this for positive utilities and positive values. And for negative values, it's going to look like that. If you're really curious about what this is going to look like, and you really want to apply expected utility theory to some of these cases, go plug this into Google or into Mathematica or Wolfram Alpha, wherever you prefer to plot your diagrams, and see what the utility function looks like. But it's basically going to be like this for positive utilities, positive values, and it's going to be the reverse for negative ones. But the basic point being, there are some utility functions that will have this property, and as long as we're using a utility function like that, we're going to get finite expected utilities. We're not going to have the problems we saw. Okay, so what do we get with expected utility theory as long as we have a utility function that is bounded in this way? We'll get finite expected utility for the act of believing in God in Pascal's wager, and likewise for the St. Petersburg game and the Pasadena game, and for the other games that we compared them to. And for a kind of a full accounting of all the problems that we then get to avoid if we do this, if we adopt expected utility theory with a bounded utility function, this is just the list of all the problems from earlier. For instance, expected utility theory won't say that believing in God in Pascal's wager is strictly preferred no matter how low the probability that God exists. It won't violate statewise dominance in Pascal's wager. It won't say that you should play the St. Petersburg game no matter the price. And it won't violate statewise or stochastic dominance when comparing the St. Petersburg game to things like the Petrograd game, and likewise for the Pasadena game with the issues we saw there, for much the same reasons that it deals with the St. Petersburg game. Okay, so that was expected utility theory being able to overcome these problems. Risk-weighted expected utility theory can overcome them too, and it just does so in basically exactly the same way. So by the same method, REU theory can overcome those problems as well. You just need to have a bounded utility function. Now you might think, well, REU theory allows us to capture risk attitudes and it allows us flexibility in the utility function and in the risk function, two different ways of capturing risk attitudes. So couldn't we overcome these problems using the risk function? Well, actually no, for somewhat complicated reasons. It turns out that if we try and adopt a risk function which removes these problems, then we're going to end up violating stochastic dominance. But you don't need to worry about that too much. The basic point is REU theory can also avoid these problems, but it has to do so via a bounded utility function. Okay, so thinking about what we've seen so far today, we have a bunch of problems that face expected value theory, and we have a solution to those problems via adopting expected utility theory or REU theory, either way with a particular sort of utility function. But remember, we also had some arguments for expected value theory. So now, putting this all together, we've got some reasons to accept expected value theory, and now, given these problems presented by Pascal's wager and the St. Petersburg game and so on, we also have some reasons to reject expected value theory in favor of expected utility theory, or REU theory. So, a bit of accounting. What are the pros and cons of each side? So, advantages of sticking with expected value theory, which we've seen in previous weeks. Expected value theory is supported by the long-run argument. So, the verdicts of expected value theory are consistent, even if we have multiple repetitions of the same act. And you might have thought that was a nice property, a nice reason to accept expected value theory. It's also supported by the background uncertainty argument. So whatever verdicts we get from the theory, they remain consistent even once we introduce uncertainty in the background. So again, you might think that's a nice property. But now, today, we've seen a few points on the other side. So advantages of instead switching to expected utility or REU theory with a bounded utility function. So the first is that by switching, we can avoid counterintuitive verdicts in those three cases from before. We're no longer required to wager for God, no matter how low the probability of God existing. We're no longer required to pay any finite price to play the St. Petersburg game, and so on. And also, since we avoid the problems we saw in these cases, we can maintain statewise and stochastic dominance with our theory, whereas expected value theory could not. And specifically, we're maintaining statewise and stochastic dominance even for acts with infinitely many outcomes. Because after all, expected value theory can maintain these dominance principles for acts with finitely many outcomes, and finite values at least. But here we can maintain these dominance principles more widely for all acts. Okay, another advantage of adopting expected utility or REU theory with a bounded utility function is that we can maintain the sure thing principle, again, for acts with infinitely many outcomes. And remember, before the St. Petersburg game, under expected value theory, gets us a violation of the sure thing principle. And if you want a reminder of what the sure thing principle is, you can go back to the earlier slides. But really, for our purposes here, all that matters is that if you take expected value theory and you're looking at things like the St. Petersburg game, you get really weird, inconsistent verdicts of swapping from one St. Petersburg game to another in a way that technically violates the sure thing principle, but independent of that, it just seems kind of silly. So that would be another advantage of switching to one of these theories. Another advantage is that we can then maintain completeness. So remember, in the Pasadena game, expected value theory couldn't say how good the game is, whether it's preferred or not preferred to some other act. Whereas with a bounded utility function, these theories can say how to compare the Pasadena game to other acts. And we haven't actually shown that, but if you're curious, go and fill out the equation, and you'll see that, in fact, a bounded utility function does mean that we can put a particular expected utility on the Pasadena game and remove the problem. Okay. I should also mention, just for completeness, that there are options other than sticking with expected value theory as we've seen it and adopting one of these theories with a bounded utility function. You could also somewhat tweak the mathematics of expected value theory to better accommodate infinite values and probabilities and infinite expected values. And there is quite a lot of recent literature on how to do that, how to compare infinite outcomes and infinite expected values. If anyone's interested in that, I can point you to a whole bunch of great recent literature. But for the purpose of, for our purposes in this unit, we don't need to worry too much about those more complicated solutions. And you can just think about this as an either-or choice between one theory or the others. Okay. Now, the question of which of those options we should go with, of whether we should stick with expected value theory or something similar, or whether we should switch to expected utility theory or REU theory with a bounded utility function, that question happens to line up exactly with the question of whether we accept a claim known as fanaticism. Now, what is fanaticism, you might ask? Well, think back to the Pascal's wager case, just to illustrate. And remember one thing that may have seemed counterintuitive in Pascal's wager, specifically that no matter how tiny the probability is that you'll get that eternal blissful afterlife, you would still be required by expected value theory to pay a high cost for it. So it may seem especially counterintuitive that you should believe in God or that you should uproot your life and act in such and such a way, no matter how costly, even if the probability is 1 in a million, 1 in a billion, 1 in a trillion, 1 in a trillion. Doesn't matter how low the probability gets, you can nonetheless be required to pay very high cost to get this extreme long shot gamble, this extremely risky gamble at infinite value. And that may have seemed especially counterintuitive. And that implication that you should throw away enormous amounts of finite value to have a tiny probability of infinite value, that's actually a more general property of some decision theories known as fanaticism. So it's not just a property of expected value theory, it's also actually a property of expected utility theory if the utility function is not bounded. So if you think back to example before with the St. Petersburg game, how some utility functions don't avoid the problems of the generalized St. Petersburg game, well, those theories too have this property of fanaticism, where the utility function is unbounded. So this general property of some decision theories, fanaticism, which is also known as recklessness, that's what it's called in one of your readings this week. What actually is it? Well, here's a precise definition. It says that for any probability p, no matter how tiny it is, and for any cost, any finite cost, no matter how great that cost is, paying that cost to have probability p of some much preferred outcome is strictly preferred over not doing so. So this says that if we have a decision like this one between some fanatical choice and some non-fanatical choice, where the non-fanatical choice gives you, say, value 100 for sure, so 100 would be the finite cost, and here the tiny probability p would be whatever p is, maybe it's 1 in a trillion. Fanaticism says that it would be strictly preferred to take the fanatical choice over the non-fanatical choice, as long as this outcome here, gaining value n, is great enough. If this is, value a million, a billion, a trillion, if it's just a big enough value, then the fanatical choice is preferred. And fanaticism says that it can be preferred as long as that value is high enough for any probability. So the probability can be as tiny as you want, and also we can replace value 100 with, however large a value you want, and there'll be some fanatical choice with that probability that is nonetheless strictly preferred to the non-fanatical choice. So for instance, perhaps this is saving 100 lives, and the fanatical choice is saving 10 billion lives, and the fanatical choice is then strictly preferred. Or if this probability p is especially tiny, maybe it would have to be far more than 10 billion lives, but for some outcome, the fanatical choice is still going to be strictly preferred. Okay, and you might recall that this looks a lot like the decision matrix for Pascal's wager that we considered, except for the minor detail that I put the cost down here rather than put it in this state, which is just equivalent. Okay, but fanaticism doesn't involve any infinite values or infinite expected values, since after all, every one of these outcomes has finite value. It merely uses the fact that the values can always be larger. So however small this probability and whatever the cost here, we can always find a big enough value, one that's high enough to put in here to make the fanatical choice preferred. It doesn't have to be infinite, but given that values can always be higher and higher, we can always put one in here that makes the fanatical choice preferred. So one thing worth noting is that fanaticism, despite sounding like this perhaps somewhat abstract claim, it doesn't just apply to weird abstract cases like Pascal's wager, you might think, but also whether or not we accept a decision theory that implies fanaticism, whether or not we accept a fanatical decision theory, has really wide-ranging and important practical implications for the decisions that we then make. So whether we accept a theory that implies fanaticism may be very important in practice. For instance, just as one kind of perhaps somewhat silly example, should a policymaker allocate funding to life-saving healthcare, which might then be guaranteed to save a whole bunch of lives, or should they instead allocate the funding that they have control over to mitigating a risk with extremely low probability, such as preventing a cataclysmic meteor strike, like here from the film Armageddon, where I think it's destroying Paris here. So the decision matrix might look like this, where funding healthcare saves 100 lives for sure, whereas funding meteor defense, there's only, say, a probability 1 in 100 million that a meteor is going to destroy the city or destroy the world or what have you. While almost certainly there's not going to be a meteor that comes to destroy the world. So almost certainly by funding meteor defense, you'll actually gain or lose nothing, you'll achieve nothing. But nonetheless, if the decision theory we accept happens to imply fanaticism, then as long as enough lives would be saved by funding meteor defense, our theory might then say that it's strictly preferred that you fund the meteor defense, rather than saving 100 lives for sure. And that might seem counterintuitive, but nonetheless, expected value theory says that you should fund the meteor defense, as long as this value is high enough. And likewise, expected utility theory or risk-weighted expected utility theory say the same if you adopt a utility function that is not bounded. So like the utility function we had before, utility of v equals the square root of v, that is a fanatical utility function. That gives us fanaticism. So on that utility function, if this number of lives was just high enough, we would get the answer that you're required to fund meteor defense. So that may seem like a pretty counterintuitive verdict, and also one that might in practice have pretty serious ramifications, both here and in other cases. Okay, so fanaticism and the theories that imply it. So expected value theory implies fanaticism. For any probability p and any cost, perhaps a cost of value c, expected value theory says that we're required to pay that cost to have probability p of any outcome with high enough value. In fact, with value c divided by p. And since p is less than 1, this is like bigger than c. For instance, if the probability is 1 in a million and the cost is 100 lives, or not saving 100 lives, then expected value theory says we would be required to pay that cost to not save the 100 lives in order to have a tiny probability of 1 in a million of saving more than 100 million lives. Whenever there's more than 100 million lives on the table that you could have this tiny probability of saving, expected value theory says you should take that. And likewise, if the probability were lower, any probability p, we would just have to make the value much higher, the number of lives you would then be saving, and we would still get this fanatical conclusion that you should take the tiny probability of saving many, many lives, or getting a great deal of value. Okay, now what about expected utility theory and risk-weighted expected utility theory? Well, they imply fanaticism too, if we have certain utility and risk functions. Any utility function that isn't bounded, combined with basically any risk function that doesn't violate stochastic dominance. But anyway, basically, if you have a utility function that's not bounded, then these theories also imply fanaticism. But correspondingly, if we have a bounded utility function combined with any risk function that satisfies stochastic dominance, then we avoid fanaticism on these two theories here. That is, for these theories, to avoid the problems of Pascal's wager, the St. Petersburg game, and the Pasadena game, like we saw before, we need a bounded utility function, and having a bounded utility function means we avoid fanaticism. So whether we accept fanaticism on these theories perfectly lines up with whether we avoid these various problems we saw earlier. So one thing you could take away from that is that, well, this is great news because we want to avoid those problems, and you might think that fanaticism is absurd, that it's just so counterintuitive that you should embrace fanaticism and the sort of verdicts we just saw. So great, we can kind of kill two birds with one stone, accept one of these theories, have a bounded utility function, and we solve both problems. But there are arguments for fanaticism, and by extension, therefore, arguments against having a bounded utility function and thereby avoiding all of the problems we saw earlier. Here's just one argument. There are several other great arguments in the literature, but we'll just focus on one here. And it goes like this. So take the two acts described by the definition of fanaticism from just before. Fanatical choice, non-fanatical choice. Here you gain some amount of value. Here you have a tiny, tiny probability p, whatever p is, for gaining some much vaster amount of value. Okay? And suppose we took this second one, non-fanatical choice, that act, and we made the value here way, way higher, as high as you like. But we also introduced just a tiny probability of getting value 0. Do you think that would be an improvement if it was a tiny enough probability of 0 and if the amount of value was high enough? So if we've got non-fanatical choice, and we'll call this improved choice 1, that's the same as above, but now we have vastly higher value here with improved choice 1, and we have a tiny probability, 1 in 100,000 of getting value 0. You might think, yeah, this is an improvement over that. After all, we don't care too much about tiny, tiny probabilities. We do care about getting a huge amount more value for sure. Perhaps this is saving 1 billion lives, winning $1 billion, whatever it might be. So you might think, yes, this is an improvement. Now, what if we took that improvement, that improved choice 1, and we again made that value far higher, as high as you like, but again, we slightly increased the probability of getting value 0. Would that also be an improvement? Well, unfortunately, it's cut off a little bit, but here again, we have improved choice 1, and now we've gone from value 1 billion up to value 1 quadrillion for improved choice 2. It should be improved choice 2. And we now, instead of probability 1 in 100,000 of getting value 0, we now have probability 2 in 100,000 of getting value 0. And you might think, yeah, fine, that's still an improvement. Again, we don't care that much about increasing this probability of gaining nothing from 1 in 100,000 to 2 in 100,000, not when we're basically getting all of this value for sure. But we can keep on doing that, going improved choice 1, improved choice 2, improved choice 3, and so on, some very, very large number of times, step by step, until we've gotten all the way down from, instead of only having probability 1 in 100,000 of getting value 0, we now have probability, say, 999,999 out of 1 million of getting probability 0 by just reducing the probability step by step by a tiny amount until we get to a much, much bigger probability of getting 0. So eventually, we've got all the way down to probability p of gaining a vaster amount of value. And this is whatever p you want, as mentioned in the definition of fanaticism. It can be super, super tiny. That's OK. And with improved choice n-1, we have probability p plus a little bit of gaining some vast amount of value, and then probability 1 minus that probability of gaining or losing nothing. And we can do one final improvement. We go from this improved choice, n-1, to improved choice n, which is actually just going to be the fanatical choice from the start, of gaining an even vaster amount of value than this, but with slightly lower probability. So it's now probability p, and the remaining probability of gaining or losing nothing. And as you might recognize, this is just the fanatical choice from the start, with some sufficiently large n. Okay, so we've got some series of steps from the non-fanatical choice to something that seems strictly preferred, to something else that seems strictly preferred, to something else that seems strictly preferred, and so on and so forth, until we get all the way down to the end of the chain, where the fanatical choice is strictly preferred to the thing that came before it. So if each of these improved choices is indeed an improvement, each one is strictly preferred to the one that came before it. then we've got a chain of improvements all the way from non-fanatical choice all the way to a version of fanatical choice. And remember the principle of transitivity from a few weeks back, the one that was satisfied by Brienne is taller than Arya, Clegane is taller than Brienne, therefore Clegane is taller than Arya. It's not satisfied by Pokemon types, where you can have fire is super effective against grass, which is super effective against water, which is super effective against fire. So if we assume that preferences over acts are like heights, that they just go in the same direction, we can't have cycles, they're not like Pokemon types. If we accept transitivity, then we can combine all of these steps in the chain. As long as transitivity holds, and if each of these improvements is an improvement, then fanatical choice must also be strictly preferred to what we started with, the non-fanatical choice. So we can simplify the chain. Whatever we started with, if every single step is a strict improvement, then fanatical choice at the end also has to be a strict improvement over what we started with. And therefore, we have fanaticism. And this comes from one of the readings this week by Beckstead and Thomas, where they also discuss some of the other arguments. Some of the other ones I think are perhaps even more compelling than this one, but this one's relatively straightforward to see how it works. Okay, so if we wanted to block this argument that they've given here, there are only really two premises in that argument: transitivity and the claim that each of these can be an improvement. So to block it, we must deny either transitivity. We have to deny that preference works like taller than, rather than working like Pokemon types. Or we could deny that these are all improvements. We could deny that we can make an improvement each time by vastly increasing the value if you win and slightly decreasing the probability of winning. Now, I'm not really going to discuss the idea of rejecting transitivity. We actually come back to that I think in week 7, so the very next lecture. But let's instead focus on this second premise and consider what it really takes to deny this. Well, denying this also has a name. It's known as timidity. And consider what timidity actually means, what it involves. It means that there is some probability p, which doesn't have to be tiny. It can just be any probability p. And there's some outcome O, such that getting that outcome O with probability p, whatever it is, and otherwise getting an outcome of value 0, but getting outcome O with probability p is strictly preferred to getting any outcome at all, no matter how great it is, any outcome O plus, with slightly lower probability p minus a bit, or p minus epsilon, we could say. So getting outcome O with probability p is strictly preferred to getting anything vastly better with slightly lower probability. No matter how tiny the gap in probability, nonetheless, we prefer to have outcome O with probability p. Now, that may have sounded somewhat abstract, so consider what that would look like to accept this, to accept timidity, and effectively to deny this second premise. So we would have some pair of improved choices in that chain of one act after the other, one improvement after the other. We would have some act, like improved choice 1, that has probability p. Here it's very high. It's that probability plus this probability. You have that probability of gaining value 100. So outcome O is one where you gain value 100. And timidity says that this has to be strictly preferred to this, to improved choice 2, even when you've reduced the probability of winning, of gaining value 100, by just a tiny little bit. It can be as tiny as you want, some tiny epsilon, like 1 in 100,000 here. And then no matter how much you improve the outcome if you win, you might make it value 1 quadrillion. You can make it as high as you want. Nonetheless, improved choice 1 is strictly preferred to that. That's what you need to say to accept this. That's what you need to say to deny this premise of the argument. And perhaps ironically, this sounds awfully similar to fanaticism. You're effectively worrying a huge amount about a tiny, tiny probability or a tiny difference in probability. You care more about what happens in this tiny probability than you care about over here. You care about how much value you're actually very likely to get. So timidity is actually similar to fanaticism in that it involves caring more about a tiny difference in probability over seemingly all else. To accept timidity, to deny this premise, is to be fanatical about tiny differences in probability in a certain way. So you might think, oh, that seems problematic too. So effectively, you have to choose between fanaticism and timidity, this implication here. And either way, you've got to be obsessed with some tiny probabilities. It's just a question of which tiny probabilities you're obsessed with. And both may seem problematic. So the argument we've just seen for fanaticism goes basically like this. First premise, transitivity holds. Second premise, timidity is false, as you might have strong intuitions that it is. Therefore, fanaticism is true. And with the sequence of acts, improved choice 1, improved choice 2, and so on that we saw before, actually these premises are enough to get you to fanaticism. And remember that if fanaticism is true, then we can't have a bounded utility function. We can't use expected utility theory or REU theory to avoid all of the problems we saw earlier on. So even if we reject expected value theory in favor of expected utility theory or what have you, if fanaticism is true, then we're going to have all the same problems we saw with the St. Petersburg game, Pasadena game, and Pascal's wager, or at least a version of Pascal's wager. So we really are kind of in a pickle. And if we go back to our accounting from earlier, before the two options we were comparing were keeping expected value theory versus adopt expected utility theory or REU theory with a bounded utility function. Well, these correspond to the options of accepting fanaticism and denying fanaticism via that same approach of expected utility or REU theory with a bounded utility function. And we have the same kind of advantages and disadvantages as before. So the long run argument and the background uncertainty argument, they give us expected value theory, and expected value theory gives us fanaticism. So one advantage of accepting fanaticism is that we don't need to throw out those arguments, or we don't need to deny the premises of those arguments. But now, as we've seen with this further argument for fanaticism, there's this further advantage that accepting fanaticism allows us to maintain transitivity and reject timidity, which you may have thought was counterintuitive, so you want to reject it. And on the other side, we have the same list of advantages as before. So there really is a bit of a dilemma here. There's a bunch of advantages of accepting fanaticism and accepting expected value theory, and there are a bunch of advantages to this other approach of using expected utility theory or REU theory to deal with these problematic cases here, and thereby also deny the notion of fanaticism. And the question here of which way to go, of denying fanaticism or accepting fanaticism, of succumbing to the problems of these problem cases or avoiding those problems, that's been a really animating question for the last few years of research in decision theory among philosophers. If anyone is interested in writing their final essay on this topic, I have a bunch of further readings I could recommend to you, but if not, that's okay too. And you can still see that there really is a genuine philosophical puzzle here of which principles we accept and which principles we deny. And depending on which answer we take, we're going to end up with very different practical implications of our decision theory. So thinking back to the meteor case before, if we go this route, then perhaps as policymakers, we're going to put huge amounts of resources into combating low probability risks like meteors, whereas via this other route, we're perhaps not going to do so. So potentially enormous practical ramifications to how we answer this dilemma here. Okay, that's all we have for this week. I look forward to seeing you all on Friday.